Hey guys, today we're looking at logarithmic functions, and these are going to be a little longer notes. They're roughly 2 days of notes. We're going to put them all together here because there's kind of not a great break. Taking some things that we already know, like finding inverses. This time we are using logs or solving inverses with logs. So remember, the first thing that we do is we flip the x and the y when we are finding inverses. So this would look like x equals log of y base 2/5. So then when we switch this around to solve for y, we would get y equals 2/5 to the x power. And since we're talking inverses, we could use our y inverse. So that's how you would find the inverse of that. It's 2/5 to the x equals y. You could also go ahead and rewrite this by solving for x. So x equals 2/5 to the y. And then if you switch those x and y's like you're supposed to, then you get the same thing. So either way works. Typically we just switch the x and the y first. All right, so in this one, since we have natural log, we know that our base is e. I'm going to go ahead and switch the x and the y. So if my base is e, then I have y minus 10 is equal to e to the x. And so then I need to add 10 to both sides. That 10 is not up in the exponent, so I have y equals e to the x plus 10, and that would be y inverse there. Okay, so then when we graph inverses, we know that we're switching the x and the y. It's a reflection over y equals x. So remember, when you graph your exponential functions, that they go through 0, 1, and 1b. So over here with logs, they go through 1, 0, and b1. And you'll notice that both of these are talking about the same thing. We're talking about where b is greater than 1, and then we're talking about where b is between 0 and 1. So we're not going to have much scale here since we don't know what our b value is. So for this first one, I'm at 0, 1. Exponential growth, which is what this first one is, looks like this. So then if I'm reflecting over the y equals x line here, then I'm at 1, 0, and it's going to do the same kind of thing here. So it goes like this. It just reflects. All of those points are flipped. Notice we have a vertical asymptote here at x equals 0, so I didn't cross that y-axis on that inverse. Very similar on here. I'm at 0, 1, and 1b, but remember that when we're talking decay, it looks more like this. We're flipping over this y equals x line, then everything flips. So we have a vertical asymptote. We're going through 1, 0. So it looks like this. Okay, so transformations. The line x equals h is the vertical asymptote. The domain is anywhere that x is bigger than h. So just like if you were not moving, it would be anywhere that x is greater than 0. That x equals 0 was our horizontal asymptote. So now if we move to the right 3, then it's anywhere bigger than 3. Range is all real numbers. So remember, we could write these as h to infinity, and we could write this as negative infinity to infinity. So, and if you think about it, your domain of your exponentials is all real numbers, negative infinity to infinity, and then your range had those restrictions. So we've just flipped that around now. Those transformations should look familiar with that h and k there as well. All right, so we are graphing log of x base 0.5 plus 4. The first thing I do is start to look at the inverse of this. So, and I'm not looking at the transformation. So if I have 0.5 to the x equals y would be my inverse, or I could just say 0.5 to the y equals x, and that will help me to come up with some points. And then we need to transform it. So remember that one of our points is going to be 1, 0. And then our other point that we know is going to be at our base 1/2, 1. So over a distance of our base and then up 1. You can put in more things. So like 0.5 to the negative 1, if y is negative 1, 1/2 to the negative 1 flips that over. So that would be 2, if that helps you to see more points on there. We are moving then, we're not moving left or right, we are moving up 4. So our new xy would be 1, 4. It would be 1/2, 5. And then it would be 2, 3, if you want to make that separate table. Here is my xy axis. So I'm going to plot. For sure you need your 1, 0, and then you need your B1 value. And then if you want another value to -1, that's what this would look like. So then if we've just moved up 4 from here, notice our vertical asymptote hasn't changed. So we're at 1/2, 5, and then we're at 2, 3. So domain here would be anything greater than 0, so 0 to infinity. Range would be -infinity to infinity. We can get any values out. There's no restrictions on our y values. We're going all the way up the graph, all the way down the graph. All right, let's try this one. So our points that we have, you know, are 1, 0, and then our base 1. If you want more points, you could write this as 2 to the y equals x. So if we plug something in for y, like 2 to the 2nd power would equal 4. You're welcome to plug in as many of those points as you want to help you out. And then notice that we are moving left 1, up 3. So left 1, up 3. So if I plot these points, so for my original, I'm at 1, 0, a base of 2, 1, and I'm at 4, 2. It looks like this. And then when I've moved 0, 3, 1, 4, and 3, 5. So if I've moved to the left 1, my new asymptote then is also going to be left 1. So it helps to draw that in as you're graphing. So that means domain, I can plug in anything greater than -1 all the way up to infinity, and range has no restrictions. All right, graphing calculator activity. We're going to table this for now. We're going to come back to this after we've talked about properties of some logarithms, which will be in the next section. So just skip over this for now. If you have it in your notes, don't worry about it. We'll get there. So example 5 says the Richter scale is used for measuring the magnitude of an earthquake. The Richter magnitude R is given by this function, where E is the energy in kilowatt hours released by the earthquake. Graph the function using a graphing calculator. Use your graph to approximate the amount of energy released by the 2005 earthquake with Richter magnitude 4.1. So this is one we can do because we don't need to work with a change of base formula to be able to graph in the graphing calculator. So go ahead and pause the video, type in that equation, the 0.67 log times 0.37e. You'll use x as your variable and then plus 1.46. What I notice is that this 4.1 is the Richter magnitude. Richter magnitude is R. So that means that 4.1 belongs here. So I'm going to type in y1 as my 0.67 log of 0.37x plus 1.46. And then I'm going to type in y2 is 4.1. Now they give you a hint on the x window, count by 5,000. So that means x minimum to x maximum, you'll want your scale to be by 5,000, which means that we're going to have a pretty big value here. So you may want to try a few different things, but x minimum probably doesn't need to be very small because it's probably not going to be a negative value. So you can do whatever you want here, like -100, or 0 even, but your maximum, I would start at, you could do 100,000, you could do 50,000, whatever you think you need to find that value. And then your scale, this is all under window, it says count by 5,000. Now, y minimum and y maximum are a little easier to determine what you should do because you know and I put 4.2 here. This should have been 4.1 for our Richter magnitude. You know that magnitude is going to look like this, that we want to find where this logarithm and this line meet up, and this y value is 4.1. So I need my y value scale to see that 4.1. So you could do 3 to 5. You could do 2 to 6. You could do 0 to 10 if you want. But you know you want to just see where that 4.1 is, so you don't need to see a big value on your y's. Your x and y scales don't need to match. So your scale there on y's can just stay in ones. You can do it by halves, whatever you'd like to do. When you plug all that in, you're going to go into second, calc, intersect, and you will get 23,555.742. And so that's the amount of energy released in kilowatt hours with a magnitude of 4.1. If you need help with that, let me know. We can go over it in class. Just tell me. So, given that both of the following graphs are translations of the parent function y equals 2 to the x or y equals log of x base 2, write an exponential or logarithmic function to model each graph. So this is something that we've had to add recently in the past few years. And so you are just looking at these following graphs. This one and this one are your only two options for parent functions. So the first thing you're going to do is identify, does this look like an exponential graph or does this look like a logarithmic graph? From there, you're going to say, okay, now how is it translating from what I know is my parent function? How does it move? So when I look at this one, it's starting off relatively low and then it's skyrocketing in the air. That to me looks like an exponential graph. So I know that I'm starting with y equals 2 to the x. It could have told you we were starting with y equals 3 to the x, y equals 5 to the x, anything. It's just telling you y equals 2 to the x. Well, if I graph y equals 2 to the x, I know that I'm at 0, 1. And then I'm at 1, 2. So that's my parent function. So how have I moved from that parent function to this new function? And it looks like these points match up directly with the given points here of -2, 4 and -1, 5. So how did I get from 0, 1 to -2, 4? Well, I've moved left 2, and then I've moved up 3. So then I'm going to use y equals 2 to the x plus 2 and plus 3. And so that tells me left 2, up 3 is my transformation. So this is your answer. All right, this one to me looks more like a logarithmic function. So I know that I'm dealing with y equals log of x base 2. So you can use your standard points there, which remember you can write it as 2 to the y equals x if you don't remember. So we would have 1, 0 would be one of those points. And then we would have 2 to the first would be 2. So we would have 2, 1 would be your other point. And so it looks like this. So if I'm at 1, 0, and I'm at 2, 1, but here I'm at 2, -2, and I'm at 3, -1, how have I moved? It looks like I've moved right 1, and then I moved down 2. So now I have y equals log of x minus 1 base 2, and then minus 2, down 2. So there's my new function for that one. All right, guys, that's all I have to cover for this set of notes. If you have any questions, come in and see me. Otherwise, I will see you in class.